this thing. You okay?
I'm fine. How are you doing?
Okay.
Good.
Nice room.
Yeah, isn't it? It's very cozy.
Did you bring all the stuff?
Yeah.
Oh, gosh. Oh, I know.
I'm arranging. Yeah, I gotta do something.
I probably shouldn't have this Pepsi.
What's sweetie?
Probably shouldn't have the Pepsi.
Yeah.
It's okay. I don't think it matters.
So you're not a doctor until this is over?
Yeah.
Okay. You think he's a doctor now, don't you?
Yeah, he was a doctor when he was born.
Yeah.
He was a doctor when he was born. Well, when you become a doctor, can we call you that? Doctor.
Doctor. Yeah, that'll feel a little more time.
Didn't I tell you?
You should get Laura can be doctor.
Is she? Yeah, that's right. She is.
Dominic spent a summer in Thessaloniki when he was in law school, and there was a doctor that was their teacher, and he was two doctors. So he made them call him Doctor.
Did they really?
Yeah.
Really?
It's one of his favorite stories. He was in Thessaloniki.
Why was he in Thessaloniki?
He took a course there when he was in either law school or undergrad. And he knows how to say one word, panapostimio, which means college. And he always talks about doctor. Little pretentious.
Okay, so the sound doesn't work. Okay.
Does it work?
You guys are being recorded right now.
Oh, good.
That's all I wanted.
Do you have the site yet for the,
Yeah, I'll send it to you right now.
Okay, thank you.
It's up. It actually records the whole thing, I think.
Okay.
So it should be, you can go back.
is it
Go back
live
and get it
stream?
later?
It's live too. Yeah, you can go back and watch it later.
Okay.
Oh, then I can try to figure out what you said.
I hope I explain things though. That's
Are you gonna do it?
You do, you always do.
You're
You've
gonna do it
always-
on like a 6th grade level?
Yeah, that's how I
Okay.
start, and then there's still some complex stuff because like I have to
Alright.
do, but I try to start like pretty basic and then kind of expand from there.
I think you
that
should be a
everyone can
teacher.
Understand. Hopefully. Let me.
Okay. hate when these things figure it out.
Why don't you get an iPhone?
I got one and I took it back. It wasn't an iPhone. It didn't work. I couldn't do any texting because it wouldn't work.
If I can get something to work, you can
Well,
get
if I
something
can
to
talk
work.
like you do, that would work.
They all have, well, start with an iPhone 5.
All right. At least if I.
Yeah, and they have a little microphone. You press it. And you gotta watch what you send though. I've sent some pretty weird stuff.
Can I watch what you say?
Yeah.
Why? It's recorded.
No, because it says different things.
Okay.
I mean, once I told Mary Cole I watched some movie and I said I love Michael Caine, and it said I love my cocaine. And she said, "What? You love cocaine?" I said, "No."
Please look at your door.
Okay, I just sent you the link.
Thank you.
Did you get it? You can actually click on it.
An
see if it's
email
live.
or
Email. So with the Gmail. Can you get Gmail on you?
yeah, nothing yet.
It'll come.
Here it is. Live stream.
If you click on it, I want to see if it's live streamed via your phone. I think it should be. So on my computer, it looks like it should be on this page.
Okay.
Should go back. Why don't I get back?
Engineering yeast. It's there.
Is it there?
No.
I don't know this page.
You don't? Live stream. It's recording us.
Well, don't use the sound because then it's like back.
What?
It should go like, because then that'll pick it up and then it'll go back.
Okay.
But it looks good. It sounds good.
Yeah.
Okay.
So after you do your thing, we leave, and then you have to have the professors.
They ask me questions, I think, and then
I was telling Val, I did one of those when I was an undergraduate because I was in this honors program. And I was really worried about it. I get there, and the only thing I remember about it basically was that you were worried because I didn't use the right format for my footnotes.
Oh, that's so silly.
Give me a break.
That's so annoying. They are kind of sticklers, at least the library is, for like how you do your formatting.
Yeah.
The document.
So. The whole thing, that's what I remember.
Yeah, that's all. That's the take-home message.
I didn't use the right format.
Hello?
He won't know how to do it. We'll look at it later. I'll get it. Send it to me.
Why don't you video record this on your phone?
No, you don't need to. Who's that? Who texted?
David.
No, you don't need to because it's on.
Yeah, you can look at it.
You can look at it.
Send me the link.
Yeah, send.
Send you the link?
Yes.
Yeah, because then we will watch it later.
Hey, I just sent you the link. Did you get it? It's on your BMW account. Yeah, I should have called you. Yeah, I just sent it, so it should be on that. No, because it's already video recorded. James is having it recorded.
It's a live stream.
And I would be in the way, trust me. So, yeah. Text me if you don't see it, because I pulled it up on the, okay, all right. How does it look?
I think it's right.
The, okay. Okay, open the, okay, all right, bye, all right. Enjoy your son, don't talk to me. My son doesn't want me to bug him. He's like, why are you taking stills?
You can taste.
Because I want to take stills. And I'm going to send this to you, to your home account.
Okay.
Ms.
What is it?
Ms.
Let's see how many people are watching. 2 people are watching the live stream. Wow.
Oh, there you
A lot
go,
of
there you
people.
go.
It's probably David and Deb. I sent it to Deb.
Oh, Deb's got it too.
Maybe Caitlin. Dan.
I sent it to Dan and Q.
I saw that. Yeah, good.
Okay. Yeah.
Oh God. Do you think?
So someone, Suzanne from the computer facility should come in soon for the. She's gonna set something up for filming it tomorrow.
Okay.
So that's like in case this fails.
Do you think Dan will call in a question?
Maybe you can tweet them in. Did you see?
Yeah, I saw that.
You can
Tweet the
tweet in a
questions
question.
in.
You can also comment in the box below.
Oh,
In the YouTube video.
maybe we should do that later.
Yeah, if you want. Let's see. If I stand here, I think it.
Do you want us to ask a particular question?
No. Only, yeah.
If you have one, you know. Do you have any questions, Gavin?
Um,
Why did you come here?
what's a genome?
I give a good analogy, so hopefully.
Okay.
I don't want to
He's lived with,
ruin the thing.
he knows how to dumb things down. 'Cause
Okay.
He's had to
Right, so-
explain things to me.
Okay.
What time will you leave tomorrow? 2?
One something, yeah. Just, we'll take a real Uber.
Take a real Uber.
Or a cab, doesn't matter. It's not rush hour, so that's all it
That
matters.
helps.
I hate rush hour.
Any time of like, 'cause I should be able to get home before the traffic is too bad.
Yeah, we'll get you home and then the car and just get right on the road. It'll be good. You sleep okay?
Did you find the room okay? Was it okay?
No,
Yeah, no problem at all.
no, I think you could recommend that place.
Oh, no, he meant this room.
Oh, this.
Oh, the hotel one? Yeah, the hotel one's fine. I knocked the sliding glass door off the thing.
Yeah, you broke the.
I didn't
Shower
break
door?
it. No, I didn't break it. No, there was no shower door. It was,
Shower curtain.
no, the suitcase was in the way. You know. Nothing special.
Noodles.
Oh.
Thanks, so.
I guess you should. It's got 35 minutes. It'll be done. Once you start, it's all over.
Yeah. Okay, let me me sign this.
Hi, how are you?
Good, how are you?
Good. Are you Suzanne?
I'm Suzanne.
Oh, I'm Jenda's mom.
Uh-huh.
You said you were gonna set something up.
Yeah, I'm setting up the video camera.
Okay. If we need to move, let us know.
Yeah,
You
let us.
don't need to.
Okay.
I may ask you to stand in for him if he doesn't show up soon.
All right.
Okay.
He just went to the restroom.
Oh, that's no problem.
Unbelievable. What time did it start?
Who's it, Deb?
Yeah. It starts at 11. Tune in. See, it's at 11. Tune in. Suzanne's here.
Oh, she.
Yeah, she's gonna,
Oh, okay, cool.
she went out back.
Okay. Did you see the flyers up for my defense? You should take them.
No, where are the flyers?
There's some flyers up. I can.
Oh, yeah. Deb can hear us.
Oh, good. Hey, Suzanne.
Yeah, how are you?
Thank you so much for setting this
Oh,
up.
and actually-
Hi, Deb.
Hi, Deb.
Oh, you can? Oh,
Hey, Deb. Can you hear us
Thank you
now?
so much.
So if you have somebody else around, that would probably be better.
Okay, yeah.
Hey, David, can you hear me?
Yeah.
Do you need help setting up?
Yes.
Okay.
I'll let you know if I can't get these things open.
Hey, David, can you hear us on the YouTube thing?
Well, they're not tricky so much as sometimes people do it tight, so
Oh,
it's
yeah.
hard to do.
Okay.
It's like getting the tire off your car.
Oh, yeah.
They put it on with, and then we'll need to set the camera up
Okay.
so that we catch you properly.
Oh, yeah, that's true. Okay. I'll try to stay in one place though, so you can.
Well, yeah, if somebody's monitoring it.
Yeah.
then- It's too, no, that's not.
Oh, you did.
Yeah, we want it level, otherwise you end up looking a little bit weird.
Okay.
Sort of like there's an earthquake on or something. But, you know how they used to do earthquakes in the old days?
Mhm.
They shook the
Oh, you just
camera.
took the camera.
Yeah. Yeah, that's right handed. Of course, that doesn't give quite the right effect, having been in one.
Oh, you've been in an earthquake?
There was one, about a 1 on the Richter scale.
Oh, really?
Earthquake a couple of years ago.
Oh, yeah.
And I was in a conference room and the table rippled.
Really? Oh, wow, so you can actually see that. That's pretty cool.
Because you don't think of a table able to ripple.
Mm-hmm. Wow, that's pretty cool. That's the right level of earthquake to
Right.
be in too. You don't want to be in anything more than one.
No, you don't. But New England is actually quite active, just like a gentle old lady. It moves carefully.
Kind of like me.
This has to do with the fact that they've got some of the oldest stones in the world.
Oh, really?
Yeah.
And the oldest one. Oh, did you get your flyers?
No, they're up there. You-
Okay.
Okay, there we go. Got
Okay. No, I'll go with you.
In the restroom.
No, I'm gonna get a flyer.
it. Yeah, we are not straight.
Oh, they're all sold out.
No one's gonna take them. They're not like, they're just the one. I mean, the thing is, after today, they'll try out if you want. If you want to see it later. Oh, if you want any coffee too, or any pastries, feel free to go for it.
That's always a question. should have borrowed Kenji's extension cord as well. You go with the cord you've got.
Yeah.
People will just have to, this is church lab, they're intelligent.
They'll figure it out.
I mean, that is the hallmark of the church lab, other than not doing anything that's ever been done before.
Oh, yeah, that's a nice thing too.
Well, you're scientists. Or as we used to say, never tell a scientist they can't do something.
That's a nice thing.
Were you here when they lowered the temperatures to 68 degrees?
No.
This would be about 2008.
Uh-huh. Oh,
And
no, it
they
wasn't.
declared it over Christmas
Oh, yeah.
break,
Uh-huh.
so it came back without telling people.
Uh-huh.
And what happened is people came in and the temperatures had been lowered, which was disastrous for some experiments.
Oh, yeah, I can imagine.
Because,
Anything at room temperature.
yeah,
That stuff.
especially the stuff was supposed to be at 72.
Oh, yeah.
Let's see, I'm not straight. Let's see which way.
That does sound disastrous.
So within 2 days, what is the temperatures are all centrally controlled.
Mm-hmm.
Within 2 days, people were putting boxes of dry ice over the thermostats.
Oh, really? Yeah. To trick it.
To trick it, yes. Okay, no, I'm not straight. This doesn't. Higher.
You took one?
There was a second one.
Okay.
Go back.
Kathy found the second one. Where'd you get some coffee? Where'd you get some coffee? No, thanks.
Wants to watch it, but I think you probably didn't know how to set it.
All I have to do is click on it. The link. I sent it to you, Ms.
And you at the same time.
Oh, cool. Awesome.
I could send it to his email if you give it to me.
Okay.
All he has to do, does he has an iPod, right? iPad?
No, it's got a computer at home. Hey, how are you? Okay, we're at James, waiting for James to get started. Send it to your email and you just click on the link if you want to watch it. Or you can watch it later, it's going to be taped, so you can watch it. Okay, all right. Well, no, yeah, James says he's going to dumb it down for people like us, so. Yeah. He says you need to dumb it down a lot.
Uh-huh.
All right.
How
Okay,
close to the
we'll just
top?
do it later.
Sorry, are your, how close to the top of your slides?
We'll do it later.
We need the
I'm
top
gonna send
of
you
it.
the link if you don't mind. We can
See,
get ready to go.
what I'm seeing is in here, and I'm trying to line it up so that I get,
Oh, that should be fine.
that should be fine.
Yeah,
Okay.
definitely, yeah.
And then I just
All right,
won't change the focus,
Talk to you
because
later.
I can
Okay.
go over here and pick up you.
Oh, okay, cool.
Yeah, what we like about this camera is it does handle both dark and light.
Okay.
Yeah, that's awesome.
Okay, it's going to a memory card,
Okay, all right.
which is empty because I emptied it this morning.
Okay, cool. Thank you.
And let's just show this. This is the start recording.
Okay,
You press this and then press it again to stop it.
okay, all right. And if it's recording, it's a little light.
Let's see if I do this.
Oh, okay, a little red. Okay, great.
You see the little numbers are coming back and forth.
Awesome.
I'm happy.
Cool.
And you're happy. You're really
Cool.
So we just recorded a little something or other.
Okay, a little bit, yeah. All right, cool. Thank you so much.
So I'll stick
Okay.
around because I can be here till about 11.
Okay, great. Yeah.
But we get you started.
Yeah,
George's
that's great.
introduction.
Yeah, that's awesome. That's
Yeah.
important. Okay,
That's
cool.
important.
Thank you so much.
Especially after, hearing, Steve McCarroll's introduction to Jesse Gray.
Oh, wow, that's a cool one. Yeah.
Yeah.
That's super cool. When was that?
Well, Jesse was giving his job talk.
The job talk? Oh,
And
cool.
it's- apparently they've been in the same lab when Steve was a senior, was a postdoc, and Jesse was beginning grad student.
Oh, cool. So then it's a they knew each other well.
He was well known in the lab, generally considered to be
Over here?
this way out guy who did weird stuff that nobody understood.
That's a pretty, that means a lot. That's very cool.
Their PI referred to Jesse's infernal machines.
James, are those dissertations over there on the shelf?
Are they? I don't know. I think they are.
Were they left over for somebody else or for you?
Oh, no, are these no, these are, yeah, they are, I think.
That's what it looked like.
Yeah.
Suzanne, have some coffee.
I may take a donut.
Have a
Okay.
donut. James brought them in for you. Butter people up.
Make your committee agree.
Yeah.
I figure they already have.
Yeah, I hope, I don't know. Yeah, I guess that's kind of how it works.
No, they wouldn't let you get this far if they haven't.
That's
true.
Hi, Sophie.
Hi, I found it. Congratulations.
Thank you. How are you?
How are you?
Good to see you.
Hi, how are you? Who's on stage with your husband?
Nice. There's, you know Kathy Black?
Hi, nice
My
to
friend
meet
Kathy
you.
Black. I work with her. So sit next to me.
Okay.
No boys, huh? Tonight, maybe.
Michael, yes, I'm.
How are you doing?
I'm okay, how are you?
We were in a call this morning to Greece.
Okay,
Oh, how did that go?
so here,
Interesting.
Really?
It's very interesting.
It's very interesting.
You don't want to know.
Don't worry, you won't be
Everyone's
bothered.
on a call together.
I have PTSD from it.
Okay, thanks.
I had to write that in Greek.
Well, good, thank you so much.
It wasn't that easy with all the I's and the
Oh my
O's.
God, that was good. How did you get that? Do you have?
Well, it's complicated. I have a Greek keyboard on my phone for texting.
Oh, cool.
So I emailed it to myself, and then I received it on my work email, and then I copied it into.
You look happy, and why shouldn't you? I
This
sent a
is,
picture of Kathy and me at
Who did you say that
Mary Cole. Just shut up and smile.
to?
We don't look alike.
Thank God.
We don't. We don't look.
How are you?
I'm good, I'm all right.
Good. Are you gonna stop talking to me again? Don't.
I didn't stop talking to you.
oh, okay. Where's the?
Do you know what David
Okay.
Because that will be getting picked up later
Money
on.
that envelopes we can mail today.
The 2 bars.
I have
should be open.
Sophie, I don't
Okay.
have a check.
Let me see if I can get any
I
better.
don't live here.
Okay. Are you sure? Okay. That's probably okay. All right.
Just to make sure it goes right.
Oh, thanks.
You don't, you have a pointer? and
Yeah, I have a
spare.
pointer here. Yeah, and there's another one.
Oh, there's another one,
Yeah.
okay.
Yeah.
Right.
So stand with me.
And you've got your machine set up to go to sleep.
Get this photo.
Yes, yeah, that's a good plan.
We did have a speaker who did that
Oh, no.
No, it's actually 13.
every 30 seconds.
Oh, no.
You have a pen?
Yeah, I made a
Okay,
mistake.
yeah, Tin.
That's supposed to be Cyrillic.
Ερεύνα
Looks like
τα
Cyrillic.
κτήματα. Και τα χρήματα για τον Γιάννη Μερκούλης. Θέλουμε να πουλήσουμε τα κτήματα γρήγορα. Very good.
Not bad, huh?
You did great. I'll Xerox this. Do you want to sign it? No, no, then we don't want them to have our signatures.
No.
Okay, thank you so much.
All right.
when I go home, I'll put my check in and I'll Xerox everything and send it.
Okay.
Thank you.
So I don't have international stamps, I just have local stamps.
It's okay.
Okay, you got that?
I got it. This looks good. Vigo na Plomari Lesbos. I hope, well, wait a minute, shouldn't it be in English too?
Well, I figured once it gets to Lesbos with the name of Greece,
Right.
they'll figure it out.
I might put it next to it in English too.
Yeah, that's fine. As long as it gets there. I'm be done with this.
Thanks for coming. Awesome.
Me?
Yeah, thank you so much.
That's fine. And don't listen to your mother, I do talk to her. I just don't talk to her often, she wants.
Cool, thanks so much.
Oh, I didn't know it was on YouTube. Yeah.
Aim not to have.
Is the,
in the middle
Have a lot of.
of a lot of other stuff.
I think they're looking at us,
Yeah,
so they can hear us.
Yeah, but they can hear us. I got a text from Deb Silverman, who said, we can hear you. Where is it? Did you see the family downstairs?
Yes,
What family downstairs?
your family.
Oh, they're downstairs. Are they okay.
Your
Are they
dad's
coming
down-
up?
Your dad's
What about the
downstairs.
rest of them?
And there's like 4 or 5 other.
Oh, are they coming up?
What about the men?
Yeah, well, I don't know.
Probably Uncle
Cheryl,
Patrick, Gary.
maybe Rich? Are they coming up?
I should.
They was registered, they were down.
Okay.
Oh,
It
they're
takes a
getting.
minute.
Okay.
It takes a
Okay.
second.
They weren't having it. Okay, that's good.
They weren't going for coffee.
Yeah.
No, I don't think they would do that at this point.
Okay,
So
cool.
is it just?
Awesome.
Is it
Oh,
just?
there's-
You want
there's-
it on your collar?
Okay.
We actually check
I
it
can
out.
do it right
Okay.
now.
Make
You
sure
got
that,
time,
Like this.
but you're sitting here. so-
actually, you'll put it on the left,
So I
because you're
actually
probably
heard
facing over to
about
the
the
left.
Oh, yeah.
The only thing I heard was that.
And then you can put the other on your belt.
Okay, cool.
And you turn it on.
Hi, Cheryl.
You sound so.
I'm Sophie.
How are you, Cheryl? Good. How are you?
Okay.
See you. See you.
I think it's
Oh,
on.
it's on.
Hi, Leslie.
Hey, Andrea.
Yeah, she's
Let's hear
good.
She
Hello.
Dr. Howe.
Congratulations, Dr.
Yeah.
Everyone
Hi,
can hear
Ed.
us on YouTube right now.
Good, how are you, Ed? How's everything?
Good, how are you? Good. Want to sit down? Do you want to sit in the front so you can see it?
Oh, never.
You want to sit,
Okay,
you
great.
want me to move over? No, go. You want to sit in the front? Kathy's sitting there.
Kind of like that.
Oh, you know, it's
Okay, like this maybe?
We're on YouTube. Do you want me to send you the YouTube link? So that-
Yeah, that's great.
Sure.
Awesome. Thank you so much. Okay.
I want to make sure I can pick you up on the camera.
Okay. Thank you guys for coming.
Great, great.
We can be heard by them.
Everyone can hear you.
Everyone can hear me.
Yes.
Does anyone want the YouTube link?
Yeah, I'd like that. Yeah,
I think I emailed
Send
it.
it to you.
Oh, you did? Oh, you did?
Well, some people. I don't know.
Cheryl,
If they did
Leslie.
everyone YouTube. There's 3 people are watching it live right now on YouTube.
So it's
3
up?
people.
Gary, you want me to send it to you?
Yes.
So it's being broadcast on
What's
the
your,
camera
what's your
here?
email?
Yeah, 4 people are now watching.
Wow, very cool.
And you can tweet in your questions if you
Tweeting
like.
your questions?
To Scientist James on Twitter.
Oh, really? Oh,
You, Maryland.
.edu.
Can you add another address?
Sure. Let me send it one at a time. Okay.
Roach WP. @gmail.com.
I'll have to get some coffee or something if you want. Anyone, yeah, go for it.
Is it free?
No, is it free?
Is it all for premium?
It's ultra premium.
Roach WP?
WP.
P or Patrick?
Okay.
At what?
@gmail.com.
Okay.
Sorry, I haven't heard it.
Was yours like this?
Oh.
Thanks for that.
You're welcome.
It's a cozy room, I think, isn't it? It seems good. I like this room.
Wish Mom and Dad were on.
What? Perfect.
Made for the
Perfect.
Made for what?
for the fence.
Yeah.
He's gonna dumb it down for people like me.
It'll be good. I think you like it. I hope.
Okay. I sent it to you, Gary. I sent it to, James sent it to Leslie too.
Oh.
Did you get it, Pat?
I did, and I'm actually
Oh,
trying to
send it
connect right now.
to Sean.
That's good.
I could try to, what's his email? I could just send.
Oh, here it is, I got it, I got it.
Okay.
Let's see, these are okay with that good. Thank you. Kathy's a trooper.
Oh, I have it.
For what? You got some coffee?
We went to McDonald's. Our hotel is connected to the
McDonald's?
Galleria.
Oh, nice. Oh, you have
Which is
And-
connected to McDonald's.
It is connected to McDonald's.
There you go.
And,
So it's
Do everything.
we had oatmeal and coffee
At McDonald's?
at McDonald's.
Oh, I love
Good
that.
check.
So for 400 a night, you don't get the breakfast?
For 400 a night, we get nothing.
You get nothing
And
like
like
it.
it.
Like it.
And no, the bathroom's not in the hall. The bathroom is
It was one
small.
great stuff.
The bathroom is small.
It's not outside, it's in the.
No, it's not. When we got there, they had a fire drill, and they said the elevator's not working.
Did you
And you're on
really?
the 5th floor.
For 400 You didn't expect to get an elevator.
And we're like, okay, we each have a suite.
I think it's, yeah, that's it.
Sean.
Yes.
Sure, say hi to Sean. You can go. Yeah.
Is he online?
It's recording too, so
Oh
he'll
my
be
God.
there forever.
Hi, Sean.
That's it.
It's like a minute delay, so it'll take a little while.
Yes. Oh, the dead one? Oh, he's still alive.
Get pennies.
What?
Get pennies.
You can turn off the sound. Oh, there you are.
So they can hear what you were saying. Oh, God.
What?
They can hear what you were saying, right?
Yeah, yeah. Well, they is 4
Can we
people.
see that again?
But it records it too, so it'd be a YouTube video that you can go back and go back. So it records up to 8 hours.
See me again, well.
Can you go back?
Getting close.
I think the whole family should go up there and say hello to Sean.
Give an, yeah, give an,
Well,
say
that would
hello.
include you,
Tell
Cheryl.
the world who you are.
I'm not going anywhere.
I'm so embarrassing. This is not your show. I mean, this is not the hack
Oh,
show.
okay, well, I'll say hi to Sean. All right.
So, great.
Hi, Sean. It's great.
You should each do a letter, S-H-A.
Oh, yeah. Is Sean watching it?
No.
He's at work, he probably can't log on to this. We're not allowed to at work.
Figure out a way.
Yeah, I'm sure he can hack into it.
Yeah.
Yeah, I think so. I think yes. Yeah, I got it. Cool, thanks.
Is this room available for parties?
That's room available. Is that what it said?
No. Haven't seen you in a long time.
Not really.
Yeah, too.
Good.
Good, 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 yeah.
Hopefully they'll come tonight.
Yeah, that'd be great.
I'm
Go
gonna
back.
do some things, so.
Be nice.
It would be nice. Yeah, just tell them to come. Do it.
Should I invite them? That will help.
You can't say have a phone. You can't say have a salad or have soup.
I won't. You can look on here. How many people are watching now?
Watching it at the same time.
3. We went down.
We went down.
Someone went
Down.
down. Didn't want to watch it.
But I had to sign it.
It's all you. I turned it off.
The readership went down.
I just signed it, so there's one extra.
Yeah. Oh, good.
Oh, so it's false results. Are you going back to work?
No, I'm gonna go get Michael. I'm gonna go home.
This is in Ma's kitchen.
Oh, it is?
Oh, yeah.
She's back here somewhere. You could see it in the room. I took a picture of it.
Don't tell everybody Oregon.
What could it be our little secret? The whole phone, you can do the whole phone. Yeah.
Oh, my cake.
My son is wrong.
Look how. We got a lot of time.
5 people.
Does she represent you in any way?
There's 5
She's
people
like
watching
our
now.
attorney?
5 people watching.
Who has the money? Who is it?
So,
Really?
6 people, according to my thing.
Wow.
Great.
Can you tell who they are?
No, you can't.
You can't? Oh, okay.
Did you say it's Deborah?
They're at work, I don't.
It says 4 people watching this.
Yeah.
We got 6 people.
I'm just, I'm just thinking. So maybe reply.
I'll have John sign an escrow release form as well. You might have to sign it, you might have to sign it. When was this dated? Is she still representing you?
Oh my God, there it is.
Well, contact her.
6 people.
Sure,
Great.
enjoys hearing
It's good fact.
So it hasn't been released yet. Can you hear me?
So this is from the camera that's right here.
Yeah, that's that camera there.
Oh.
I have another, so one of my committee members is supposed to be Skyping in, but I don't know if he will. That's that camera. If he-
So
if he
will they
does end
be shown on the screen or?
Whoa, what? What?
Where will you see this person?
On this, there's another computer here.
Oh, okay.
Yeah.
This from South Africa, you said?
Yeah, I don't know if it's gonna work out.
This is
but-
Jim.
This is James Couch.
What is it? Is it South Africa?
What time is it? It's, I think, it'll be
10 hours.
Yeah, I think it's,
It's bedtime.
no, it's 7 hours.
7.
I sent him a thing. I think it's, 7 p.m. It'll be 7 p.m. on his side. So that's a good
That's a good
time.
time for it.
It's dinner time.
Yeah.
Just tune in.
You just think it's food.
No, you can be chewing and stuff.
Is he in Johannesburg?
I don't know. He's celebrating something. I think it's a conference.
When you start, put the code down.
But I'll put it here.
Okay.
I think you can't see it. No, you can still see it. But...
Is there a shelf under you?
Oh, okay.
You can't see it on the video.
This doesn't, I mean,
You can barely see
I need
you on
to
the
drink
video.
it. So.
Okay.
That's okay. You can't see it on the video.
Okay.
You
I think you
You
can.
can barely.
Well, it doesn't
No,
matter.
it's totally
The
up to
thing
you.
is, I don't think it matters at all. So.
Are you advertising that?
I am, yeah, I'm sponsored
Oh,
by.
you got the job, didn't you?
Oh, I see.
You can't see it at all, Val.
What?
You can't see this. You can barely see James. So you can only see him when he goes over to the screen.
Okay, that's fine.
And it's
Is
delayed by.
that?
This is the camera here.
Right.
This isn't the camera back here.
I think this is because it's at an angle.
Yeah. I want to make sure it doesn't quack.
Yeah, that's good.
Oh, his phone quacks.
This one quacks.
Who's missing a great YouTube?
Did you want coffee?
No.
I'll get it for you.
Yeah, Sean's watching.
Sean's watching?
I texted him.
Oh, good.
Does it work? Can I get those checks out?
It says 8 people are watching. Eight people.
8
8 people.
Most of them are my friends.
That's great.
Who's gonna send it?
Yes, I'm telling you, it's a social security. So we get worried about those checks out.
Yeah, but Deborah's last name is hyphenated, and she never gets her.
O'Neill Johnson.
How's that?
N-E-I-L.
You can text them too.
Yeah, I guess
Send the link to Stephanie, right, James?
So she could,
Yeah.
if she could.
Yeah, she could, yeah.
What is it, the middle of the night?
Yeah.
It's the middle of the night, but I mean, she is,
What?
it's gonna be.
You feel free.
Hey, good. How are you?
Nice to see you.
Yeah, that's.
My friend Kathy.
Hi.
This is Rich. Dr. Cook.
This is my
Hey,
sister.
good to see you.
Nice to meet you.
Oh, hi, nice to meet you. You guys can tune in via.
Definitely.
Do it at the same time.
Yeah.
Hi.
Good to see you.
Oh, yeah.
Good to see you, buddy.
All right.
Still there?
Yeah, still in Dennis.
That shooting that happened in Boston. That was that. That was the
What?
Oh my God.
Yeah, near my mom.
Yeah, it's your report.
So close. I remember going there.
Worked out. Good to see you. Good to see you. Oh, my community I don't know.
Show up.
You got possibly.
Yeah, the coffee.
Present for you guys.
Can you send me YouTube link? Deborah?
You have the menu in mind.
Because of their last names, I can't send an email. O'Neill Johnson's too weird.
It's still, they'll come, right?
Pretty much, yeah. That's, there was an old guy with a beard, he had a couple of tablets.
It's just,
It's too big.
You just have some chart.
What? That's food. Yeah.
Well, no one ever gets food for that stuff.
Well, I did.
Yeah, I actually got a.
Is yours coming?
I-
Who's Johnny?
you got the trick with me. Actually, to everyone.
Hey, Brian.
Thanks.
Hey, how's it going?
Hi, how are you? Good to see you. Hello. How are you? Congratulations. Oh, thank you.
Yeah, well, yeah.
Is George coming? I think so.
Yeah.
I could go grab it.
Yes.
Do you think maybe I'll check it out?
I like seeing it.
Yes.
Yeah, I can go. Yeah, you go grab
You know, the worst part is obviously traffic full time. It wasn't too bad. Cheryl is out. No, yeah.
Nicola, is yours like that?
If it's not traveling on that guy, you're waiting over I grew up.
Right.
2 towns away.
Right, right. Well, you kind of know the routine.
Yeah. But if you don't have traffic, it's not.
Or traffic, right.
This is like
Like
very.
this morning, yeah, I figured what we did. And we
So
don't like the,
mad.
you know, that Waze app. You see what Waze, and it reroutes you if there's traffic ahead, and that's what it is. And it was a surface route, so it was great. And so it probably took maybe 10 minutes longer than we, but we left it at 30, so that's an hour. Yeah, just else just so.
But what are we considering?
I wonder if there's a conference. I think there's a bunch of conferences. That's the one we do the Red Sox. Like, I think
Good. Yeah. Yeah, I forgot about this.
What?
You walk down from where you live.
I do, yeah.
It's fantastic.
A little less than half a mile.
Yeah.
In the winter, this winter was.
Oh,
Who else did
even
it?
if it's like
I'm done.
the pictures of you guys living
I sent it to
It's finally nice to know.
Success. Live.
I think they come. Yeah.
So Rich, how's it going?
Good, how are you? Good.
How's your brother and kids?
They're all good, yeah.
Is your mom here?
She's here, but she has a place in Rockport, so more than half the time she's up there, kind of like long weekends every weekend.
Oh, yeah, sure.
To come out to this area for the,
Jim's not here. He should be here. He said, Jim's coming in. He said, oh, did it? Hey. Oh, no.
They do that, yeah.
It's good that it wasn't like, oh, it's a video, that's cute.
You can keep your phone on to watch the thing.
You can watch it, or you can watch it on your phone.
You can tweet questions. Tweet in the question.
Oh, really?
Can they be personal?
No, I don't know how to do that. Will you ask if anyone? Can you check my Twitter to see if anyone asks a question? And
Start yelling once they.
yeah, just yell them out loud as soon as they come in.
With the hashtag.
Yeah, with the hashtag and all.
Huh?
Michael?
Just say it.
Cool. All right, we're all set.
We have all the.
Yeah, so James now he's supposed to stay in, but I think he's just gonna watch the recording.
As long as we have what we're going for.
I think we have what we're going for. Yeah, this is great.
proposing that.
I have to go to the
Okay, we're gonna get started pretty soon here. Okay, it's my great pleasure to introduce James DiCarlo. He came to us from Johns Hopkins University, where he was working. I mean, in addition to working on all his other undergraduate work, he was doing research with an old friend of mine, Jeff Bouquet. And during that period of time, from 2006 to 2010, he participated in synthesizing chromosomes towards synthesizing a whole yeast genome, the first eukaryotic synthesis, genome synthesis. And he participated in the 2 iGEM, International Genetically Engineered Machines competitions. His team winning a bronze in 2008 and a gold in 2009. And so when he came to the PhD program at Boston University around 2010 and showed an interest in our group, I was really torn. You know, he seemed like kind of marginally relevant to our laboratory. But we let him in, and there's absolutely no regrets. It's terrific. It's been absolutely terrific. He's been the core of our yeast projects from day one. I knew he was a ringer coming from Jeff's lab, and he certainly was, and went well beyond yeast, as you'll hear in its implications to gene drives. But again and again, funding agencies would say, we basically just want to fund James' work, that's it. And so he really had a big impact on our funding as well from NSF and other groups. So take it away.
Thanks, Chris. Thank you so much. Thank you everyone for coming, such people that came from far away. So the title of my defense talk today is Engineering Yeast Genomes and Populations. So it's important to start out defining exactly what a genome is. So a genome is the complete set of DNA that is within an organism, and the DNA is what makes up your genes, and these genes are organized into chromosomes, and they're found within the nucleus of the cell. And what the genome is basically a blueprint for the organism. And you can kind of think of it as like a hard drive in your computer, where all the information is stored and encoded into the hard drive. The genome is like the hard drive of the organism. So information on hard drives can be encoded into different programs, such as like Angry Birds or TurboTax, 2 very fun programs that everyone's familiar with, I'm sure. And similarly, information in genomes can be encoded into different organisms, such as wolves or platypuses, or anything really, any living organism pretty much. But what's cool about organizing information into different programs is that a computer programmer can easily take a program like Angry Birds and modify it and turn it into like a spin-off program like Angry Street, which is a parody program of Angry Birds. And people have been doing the same thing for organisms for thousands of years. And if you take the wolf, for example, people have turned that into something more familiar with the domestic dog. So if you compare those 2 modified programs, the methods that they employed to make these programs different are pretty, they're also different. So to edit the Angry Birds into Angry Street, what computer programmers did is edit the code of the program. But what people did for wolves into domestic dogs was selectively breed the organism. And there's a big difference between those 2 things, is that the time scale for editing the code of Angry Birds was much shorter than the time scale of editing the wolf. And that's because of how long it takes to selectively breed an organism. So the solution to get this a lot shorter is to selectively edit the code of the organism. And editing the code and precisely modifying the genome of an organism or a computer code allows for much quicker and predictable changes to be made. It allows you to study components, the function of the components that are already in place in the organism, and it also allows you to design new functionalities into the organism. So, as George mentioned, the organism that I focused the majority of my thesis on was budding yeast, and I'm sure most people have heard of budding yeast or baker's yeast. It's been a crucial organism for food and beverage production for over 8,000 years. Since the 1970s, it's been an important organism for industrial bioproduction. For pharmaceuticals, people have made artemisinic acid, which is a precursor to an antimalarial drug. People make various epitope-based vaccines in yeast, such as Recombavax, which is a hepatitis B vaccine. Many different vitamins are synthesized in yeast industrially, as well as recently a group, John Duber's group, synthesized one of the opioid biosynthetic pathways, so it could revolutionize some of how those pharmaceuticals are made. Also, people have made bioplastics in yeast. Since the 1960s or so, or a little earlier, people have used yeast as a model for eukaryotic biology. About 23% of these genes have very high homology to human genes. So a lot of the pathways in yeast, especially highly conserved pathways like DNA replication and repair, can be studied in yeast, and the implications can be carried through into humans. And a study recently took 76 essential genes from yeast and replaced them completely with the human homologue, and the yeast function just very well. So. And lastly, in the past 20 years or so, people have started to use yeast as a chassis or an organism to hold large pieces of DNA. And in 2009, I think it was, the Venture Group synthesized an entirely new bacterial genome in yeast. So that's another more recent use that yeast has been used for. So currently, to modify yeast genomes, you can do two things. You can modify the actual genome, which is composed of linear chromosomes, or you can modify plasmids. And plasmids are circular pieces of DNA, and they're kind of like USB drives or like floppy disks. They're pretty small, and they require selection as well, either in the form of an antibiotic gene or an oxytrophic marker. And you can see like a little diagram below with the linear chromosomes versus a plasmid that's circulating in the nucleus. An important thing to note about genomic changes versus plasmids is that genomic changes are much more stably expressed, and they're also more predictably expressed. So if you compare, this is a chart of two different fluorescent proteins expressed under different promoters, and if you look at the genome expression profiles versus the plasmid expression profiles, the plasmid ones are highly variable and kind of a mess in some ways. But the genome expression profiles are much more regular and predictable. And this is important for engineering different pathways, or if you want to precisely engineer an organism to have very predictable expression profiles. So that's one of the big advantages of engineering things on the genome. So currently, how we modify yeast genomes is we take advantage of this very powerful system that's found in pretty much all organisms, but it happens at different rates. And this system is called homologous recombination. And the basic way that this happens is it relies on pieces of DNA that are the same between the introduced piece of DNA and the host genome. So in the first step, you take the host genome and you have these homology arms, which are the same as the introduced foreign piece of DNA. This is the same sequence. So what happens is a huge cascade of proteins recognizes that these two pieces of DNA are exactly the same, and they catalyze the homologous recombination reaction, in which the foreign piece of DNA is recombined into the host genome because of these similar pieces of DNA here. And this is like designated by 2 X's often in genetics. And then in the second step, this is very simplified, but in the second step, the DNA is integrated into the host genome. And this is carried out by a ton of different proteins. So as a little, just to get everyone's frame of reference, if you look at current rates of homologous recombination in yeast, using short homology arms, about 0.001% of the cells that you put this foreign piece of DNA into will actually accept the change and integrate the DNA. When you use longer homology arms, when these pieces become even bigger, you can up it by about 100-fold. So that's kind of like where we are at the beginning of my thesis. So the goal of my thesis was to make a technique to modify genomes with high efficiency using short pieces of DNA, because short fragments can add up to large changes if you do the process over and over again. The second goal was to explore factors that stimulate the ability to engineer genomes, specifically looking at reprogrammable endonucleases that cut DNA. These are like enzymes that break the code in the DNA and allow the code to be easier to be amended. And lastly, to test the use of genetic devices that spread changes across populations. These are kind of like self-spreading code, and I'll describe all these a little more. So an overview of the talk today, I'm going to talk about a technique I designed for incorporating oligonucleotides, which are small pieces of DNA. Look at the use of reprogrammable endonucleases, and then also investigate the feasibility of gene drives, and these are these self-spreading code, they're also called selfish genes, to spread traits across yeast genome population, or yeast populations. So the first technique I'm going to talk about involves those short pieces of DNA called oligonucleotides. And we came up with a name. My collaborator who worked with on this project, Andrew Conley, actually came up with an acronym for yeast oligonucleotide mediated genome engineering, or YOGI, as a little affectionate acronym. So why would we use oligonucleotides? So just as a refresher, oligos are short DNA molecules. They're very cheaply synthesized, which is really nice because you can make a lot of them. They're the appropriate size to modify different regulatory regions or protein coding regions, so they're of a usable size that you could actually use them for genome engineering. And the changes that are made with oligonucleotides can add up. So if you have these like linear chromosomes here and you incorporate oligos, over time, if you do this many times, you can end up with chromosomes that look very different than when you started because the changes are additive. So the overview of what I'm going to mention about Yogi, I'm going to talk about the reporter systems I used, as well as the different endogenous pathways that I manipulated. And I'm going to lastly mention some of the cycling I did so that the additive changes could be studied. So starting off, I took a wild-type yeast cell and I transformed in an oligo. And transformation is just the process where you put a piece of foreign DNA into a cell. So I transformed in an oligonucleotide, and I looked for the change that was made. And the way I assayed how well the change was made is I measured the recombination frequency, which is a ratio. And it's the ratio of number of cells that incorporated the oligo versus the total number of surviving cells. And I looked at 5 different markers. So these are 5 different genes that I incorporated oligonucleotides into. 2 of them were broken, and I fixed them with an oligo, and 3 of them were already working, and I broke them with an oligo. And these could all be assayed very well. So the 2 endogenous pathways that I manipulated in yeast were the mismatch repair pathway, which deals with heteroduplexed partially complementary DNA, which is important because when I introduce an oligo, there's going to be a region that I want to change, and this region will be not exactly the same as the one in the genome. And so this pathway deals with DNA heteroduplex DNA recognition and excision. And the second pathway is the homologous recombination pathway that I mentioned before, and it's present across all domains, and it's very important for fixing broken DNA and broken genomes. So this is a little cartoon of how a mismatch repair works. So there are three main players. So there are these. The first complex is the MSH2 MSH6 complex. The second is the MLH1 PMS1 complex, and the third is XO1, which is a DNA cutting enzyme. So when you have mismatched DNA, it's represented kind of as like a bubble. So these regions are complementary to each other, but these regions are not. So they don't participate in traditional base pairing. So you have it's conceptualized as a bubble. So what happens is the MSH2 MSH6 complex recognizes this little bubble and recruits the MLH1 PMS1 complex. This then in turn recruits the exo and nuclease, which then cleaves away this bubble. And this can then be repaired by other proteins in the system. So because the changes that we were introducing into the yeast genome would create a bubble like this, we wanted to see if we knocked out these particular enzymes, if we'd have an effect on the incorporation frequency of oligos. And what we found is that when we knocked out the MLH1 gene in 3 different strains, so let me first say that we worked with 3 different strains. This is all this work's also done with Andrew Conley, who was a visitor in our lab. So the 3 strains we worked with were the BL648 strain, which is a lab strain that was reported to have high recombination frequency already. We worked with the SEN-PK strain, which is a more industrial strain, but it's also a good lab strain. And then we worked with this industrial yeast strain, this VTT strain that was originally identified as a brewery contaminant. So it's very robust and it's really cool in industrial settings, but it's a little harder to engineer. So we picked those 3 strains and we knocked out MLH1. And what we found is that when we knocked out MLH1 across all the different areas that we incorporated oligos into, so in these 2 strains we had 3 different targets, 3 genes that we incorporated oligos into. In this strain we only just incorporated into 1 gene. But we found that the incorporation frequency ranged from anywhere from 3.8 to 11-fold increase when we knocked out those genes. When we knocked out the MSH2 gene, we found that the incorporation frequency was a little less, anywhere from 3 to 9-fold increase. And when we did the double knockout of both MSH1 and MSH2 in these 2 strains, the incorporation frequency went a little bit higher, up to about 13. However, these 2 strains had a growth phenotype that was much slower, so we decided to just stick with the MLH1 strain going forward because this strain gave the highest fold increase in oligonucleotide recombination. And we stuck with this knockout going forward for all 3 strains. We then wanted to manipulate the homologous recombination pathway that I mentioned before, and this is just a refresher. DNA with homology arms can be incorporated into genomes via a bunch of different proteins. And this pathway is quite complex. And here's just one branch of the pathway involved with single-stranded DNA, in which multiple proteins are involved in the recombination. But we actually, a few papers had already reported that RAD51 and RAD54 were important in the repair using single-stranded DNA. So we decided to just focus on those 2 proteins. We also looked at a particular mutant of RAD51. There was a point mutant that also had an increased ability to recombine single-stranded DNA. So we focused on just RAD51 and RAD54. And if you compare, so when we just incorporated them singly into all 3 strains, the incorporation frequency for just RAD51 versus the RAD51 single mutant was 27 versus 80-fold, so it's about 2-fold more, a little more than 2-fold more with the mutant RAD51 in the BL6 strain. So we took this mutant RAD51 and incorporated it into the other 2 strains. And what we found is a incorporation frequency ranging from anywhere from 5.8 at the lowest up to 26 in these 2 strains. But it was much higher in the BL6 strain, actually. We also incorporated the RAD54 gene singly into this SEN-PK strain, and also saw a similar increase in oligonucleotide recombination. When we did the double overexpression of both of those genes, we found is a oligo recombination frequency ranging incorporation fold by anywhere from 20 to 500-fold. And that corresponded to recombination frequencies anywhere from 0.2 to 2%, depending on the locus in which we all incorporated oligos. So that was really high. That was much higher than anyone had reported before. So the types of changes that can be made with these oligos, we took the best strain that would recombine oligos, and what we did is we tested different types of mutations that could be made. And mismatches, which are pieces of DNA which don't have the same base that you're incorporating, and did much better for incorporation than deletions, and that's where, or insertions. So in deletions, you actually remove segments of DNA, and insertions, you insert pieces of DNA. And it varied depending on how many base pairs we actually incorporated. So with 1 to 8 mismatches, there was a decreasing homologous recombination frequency. But with deletions and insertions, it stayed around the same, and it was much lower than single base mismatches. So multiplex modifications could be made using this method if you cycle the changes, if you cycle the process. So starting with the cells that, the most recombinogenic cells, if you incorporate oligos in a cyclical way, where we start with the cells in this state here, prepare the cells and transform in DNA, and then transform the cells with DNA, and then we do this cyclically, so we start at 1, go to 2, and go to 3, and do this for 3 times. We wanted to measure to see if we could increase the amount of recombination in a cumulative way. So after the 3 steps, we would assay the recombination frequency, and then we do this cycle 3 times. And we'd assay the cumulative recombination frequency at the end of each cycle. And we picked 2 different alleles, or 2 different genes that we wanted to target. And what we found is that after each cycle, the cumulative recombination frequency increased. And so at the end of cycle 3, the recombination frequency at each locus was anywhere from 0.5 to 0.7 for these 2 genes that we targeted. And in the combinatorial setup, where we assayed the mutation frequency at both loci in one cell, the frequency was about 0.005. So this shows that you can complete this method in a cyclical way and accumulate changes over time. So you can start with something where you have a bunch of wild-type chromosomes, incorporate oligos, and over time you'll end up with a genome that is much different than you started. So as a little summary for the Yogi process that we engineered, the potential library size for this method was anywhere from 100 to 10 to the 5 recombinants per locus per cycle. And that just depends on the locus that you target as well as the strain that you use. And that's just inherent variation in both recombination efficiency at each different locus as well as the ability for different strains to incorporate oligos. And the final recombination frequency ranged from anywhere from 0.2 to 2% for all strains and loci. And if you compare the original chart we had, where we had 0.001% incorporation frequency on short homology arms and 0.1% recombination frequency for longer arms, when you have Yogi and short homology arms, you get a frequency of anywhere about 1%. So we're doing much better when you actually employ Yogi. So the second step that I took in my thesis was to look at reprogrammable endonucleases. And these are super exciting. And these come from the CRISPR-Cas system. And I'll describe all these things in a little more detail. So the reason we looked at endonucleases is because these are DNA scissors that cut within DNA strands. So they're often represented as like Pac-Man that cut, and they don't really eat DNA, but they cut it and then make a break in the DNA. And DNA that is broken has a much higher recombination efficiency. So in yeast, if you break the genome and incorporate a piece of DNA, the recombination frequency can be increased by about 4,000 folds. That's much higher. So this is a little schematic of what happens. You have your introduced DNA, and you have these homology arms that we mentioned before, and you have your genome. When you cut the DNA using these Pac-Man or DNA scissors, as they're often called, the introduced DNA can be integrated via homologous recombination, and this is stimulated because of a break. So this is a case in which you do have a piece of DNA to introduce. And then the DNA is recombined into the genome using homologous recombination. There's also a scenario in which you don't have this introduced DNA, and what happens is you get mutagenic repair. So the area in the genome is mutagenized, and the cell wants to repair this cut somehow. So it just usually either anneals the ends or puts in some bases, basically. So those are the different pathways that we looked at. So the types of the type of endonucleases that we looked at for this study were from the type 2 CRISPR-Cas system from Genomes Streptococcus. And basically, this is a bacterial immune system. So Pyogenes streptococcus is a bacteria, and it employs these cluster regulatory interspace short palindromic repeats, and that's what CRISPR stands for. It employs this system to protect itself from invading nucleic acids, such as parasitic genetic elements like bacteriophages, which are viruses. So this is basically an immune system for bacteria. So we took this system, we took several components of the system, and we put them in yeast, basically, and see how well they work. But here's a little diagram of the native system in Streptomyces pyogenes, Streptococcus pyogenes. So in that particular organism, CRISPR is a 3-component system where you have a CRISPR RNA, and this associates with a region in the genome, a transacting RNA, which coordinates with both the CRISPR RNA and the Cas9 protein, and then the Cas9 endonuclease. So all of these components come together to form a functional DNA cutting enzyme. So you need 3 components for the native system. In 2012, the Dwodna group came up with a new RNA that works just as well as the 2 previous RNAs. And basically what they did is they fused the CRISPR RNA to the tracer RNA in a particular way, so that all you need is the synthetic guide RNA and the Cas9 protein to form a functional endonuclease. So they took a 3-component system and made it a 2-component system, which makes it a lot easier to use. So here's a close-up of Cas9 in association with the guide RNA. So this is the genomic locus that you want to cut. This is the protospacer associated motif, and this is a required region for Cas9 cleavage. However, this region here can be completely recoded. So this can be any region in the genome as long as it's next to an NGG sequence. So this is, in this case, it's a TGG, but this can be any sequence as long as it's near an NGG. So what makes it amazing is that you can design DNA cutting enzyme to any locus in the genome as long as it has an NGG sequence. So this has revolutionized the genome engineering field for that reason. So what I wanted to do in yeast was validate that Cas9 was being expressed and actually cleaving DNA. And so I looked at targeted mutagenesis. And so that was the scenario in which you didn't supply a foreign piece of DNA. Then I looked at the recombination frequency with foreign DNA. And then I optimized the technique and applied it to a particular proof of concept. So this is just another diagram of Cas9 in association with the locus. And you can see the cutting happening here next to the NGG. So I took Cas9, expressed it with a particular promoter. I took the guide RNA, expressed it with a SNO-RNA promoter here. And then I took 2 different targets. I took the at the CAN1 gene. So I called them CAN1Y and CAN1Z. So they're just 2 different targets of the same gene. And they have different PAMs and they target different sequences. So what I did is I first looked at mutagenesis. So this was a scenario in which I didn't supply a foreign piece of DNA. So you should get mutagenic repair. So we should see an increase in mutation frequency at the CAN1 gene. So I looked at 2 different genes. I targeted the CAN1 gene, and then I looked at I monitored the mutation frequency at the LIPE1 gene, which is also another negatively selectable marker. So I could monitor the mutation frequency of both the targeted and a non-targeted gene. And the reason I chose a non-targeted gene as well, it was just to make sure that the targeting was specific to the CAN1 gene. So within cells, when I express Cas9, or when I just expressed the two different gRNAs, the mutation frequency did not increase at the CAN1 gene. However, when I expressed both of those components together, we saw a much higher mutation frequency that was increased by over 1,000-fold, and that depended on the site that we targeted. So that was great indication that Cas9 was actually cutting. And you also can see that the LIKE1 non-targeted gene, the mutation frequency stayed about the same. So that meant that the cutting was actually specific, or mostly specific. We then sequenced strains that emerged from this study, and we found that the mutations that were incorporated into the genome were very close to the PAM. So that was another indication that Cas9 was cleaving correctly at the specified locus. You can see you have a lot of deletions, and you have a few insertions here. And these were the two different PAMs for the two different targets of the CAN1 gene. So that was a nice validation too. So then I wanted to see if we could take this system and use it to stimulate DNA recombination. So what I did is I took a gRNA plasmid, so I expressed that gRNA component on a plasmid, which I could select for. And then I incorporated either double-stranded oligos or double-stranded larger pieces of DNA. So these are up to 2,000 base pairs. So oligos are anywhere from like 2 base pairs, I guess, to like about 200. So these are much larger than the oligos. So I then transformed these into yeast, and I looked at the recombination frequency of either oligos or the double-stranded cassette. So without the gRNA, the recombination frequency of both the oligo and the cassette were very low. However, when I incorporated the gRNA into the plasmid and looked at the incorporation of both the oligo and of the larger piece of DNA, the recombination frequency was almost 100%. So that was quite impressive, because this means that you could incorporate changes onto the yeast genome without providing selection at the locus of incorporation. So that was pretty exciting. So what I wanted to do is then apply this system to a proof of concept experiment. And I took a phenotype in yeast that could be easily assayed, and that was thermotolerance. So several gene knockouts actually in yeast have been shown to benefit stress response to high heat. So actually when you knock out these 3 genes in yeast singly, the knockout actually confers thermotolerance. So they can actually survive higher heat stress, which is pretty interesting. And the thought is that it kind of preconditions the cell to a stress responsive state. These are all involved in like very complex pathways. And then another gene I took was a ubiquitin gene. So this gene deals with marking damaged proteins for degradation. And this particular gene, when it lacks a phosphorylation site, it confers a thermotolerant phenotype. And it's thought in the same way that it's kind of preparing the cell for a stress responsive state. So I wanted to look to see if I could make changes to these 4 genes in a multiplex fashion. And that way I could look at how these genes affect each other and if they confer an even greater thermotolerant resistance phenotype. So I took the 4 genes, and I designed gRNA plasmids to target each of the genes. And I also designed 4 different donor oligos that would incorporate either stop codons, which would knock out the 3 genes that need to be knocked out, or a mutation that would remove the phosphorylation site for this particular gene. And I co-transformed all of these as a pool into yeast. And I did a similar cycle that I did before with Yogi, where I transformed the cells, I selected for the gRNA plasmid, and I assayed the recombination frequency at the loci that I was looking at. And then I cured the population of the plasmid, and I did this 2 times. And what I found is that after 1 cycle, the vast majority of the cells had 1 or more change. And then after 2 cycles, about 40% of the cells were double mutants. And I was actually able to identify a triple mutant as well. So doing serial dilutions of these strains that I identified, so starting with, I was able to get, I think, 9 different strains out of the process. They're either single, double, and then 1 triple mutant. So what I did is I took the cells and I did a serial dilution, which means you start with very dense cells up here and you do 10-fold dilutions down the plate. So just starting out with no incubation, you can see the cells kind of grow, and they have the same kind of density, where they're the same amount of cells in each different well. Then I did a heat shock at 55 degrees for 2 hours, and I plated these cells in the same way. And what you can see is that in the single mutants, as reported in the literature, a few of the different single mutants have, this one seems to have a much better fitness than the wild type cell. And then if you look at the double mutants, it looks like this one here, this double mutant SCH and TFS1 have a higher fitness, as well as this TFS1 UBC mutant here. They both seem to have a higher fitness than the wild type. So it was kind of cool. It shows that using CRISPR-Cas to make multiple changes in yeast, you can study epistasis between genes. So that's what so in studying the interaction between genes. So as a summary for the my yeast CRISPR-Cas experiments, I optimized the CRISPR-Cas system for genome engineering in yeast. And with this system, I found that you could generate libraries as high as 10 to the 5th genomic recombinants. And I also applied this technique to thermotolerance. And looking at the chart that we had before, where I added Yogi, using CRISPR, you can get recombination frequencies of upwards of 100%. So you can't get better than that, pretty much. But we always aim to it. So then the last part of my talk, I want to mention some of the work I did on gene drives, which are selfish genes to modify yeast populations. So when we want to introduce an allele or a gene to a population, the chance of passing that gene on is only about 50% unless there's selection for that particular gene. And in this case, if you take these two yeasts, for example, I first want to say that yeast, for the most part, reproduce asexually, so they just divide. However, you can get them to mate sexually as well. So for the last bit of the talk, I'm going to talk about yeast that I'm forced to mate sexually. And it's not that hard, but it's just not what a lot of people do. So when we want to introduce, so the chance of passing on this particular trait, which is what we'll call this like the red trait, the chance of passing it on is only about 50%. However, when you have a population that's mostly yellow cells, what happens to the red trait is over time it gets diluted out in the population. So one of the challenges with rare or engineered traits when trying to modify population in sexual populations is that they get diluted out if they're not selected for. And that's where gene drives come into play. So gene drives are selfish genes that bias their own inheritance. And one method that they employ to do this is with endonucleases. And what we wanted to test is that if we could use CRISPR endonucleases, so the system I described before, to make gene drives. So if you take this example here, where you have a gene drive wild type, a gene drive parent, and you cross it with a wild type parent, what happens is the progeny should have one copy of the chromosome from the gene drive parent and one copy from the wild type parent. What happens with the gene drive is that an endonuclease in the gene drive is expressed, cleaves the wild type locus, stimulates homologous recombination between these two loci, and the result is a gene-driven prodigy. So the result is a homozygous gene drive progeny. So if we look at that original cartoon with the red yeast and the yellow yeast, if you had the red yeast's allele, or the trait encoded by a gene drive, what would happen is the progeny would be biased to have the gene drive trait, so greater than 50%. And over time, even if it was mating in a population that was mostly wild type, over time what would happen, we'd hopefully get the population being taken over by the gene drive. So these are very powerful and very interesting. And we wanted to test if we could make these using the CRISPR-Cas system in yeast. So basically, they call them gene drives because they can drive genes through populations. That's where the drive comes from. So safety is a very important consideration when working with gene drives because they have this ability to drive through populations. So we took two different approaches for safety. And the first approach was separating the Cas9 protein from the gRNA. And if you remember, the CRISPR system is a two-component system in which you have the gRNA and the Cas9 protein stuff. So it as two separate components. So what we did is encode the Cas9 protein on the plasmid and incorporate the gRNA into the locus. And what the gRNA effectively was the gene drive itself. So the reason we put Cas9 on a plasmid was because plasmids can be, if they're not selected for, are eventually lost in yeast when they reproduce either sexually or asexually. So this was important in case of the worst case scenario when some of these strains got into the wild. Over time, they would lose the Cas9 plasmid and in fact lose the ability to drive the gene drive through the population. So we did a really cool proof of concept experiment where we took the AID2 gene and designed the gene drive to knock it out. And we chose the AID2 gene because of this really cool phenotype. So when cells have an AID2 gene, so when they're prototrophic for AID2, they are white. But when they have a knockout of the gene, they are red. And this is because of a accumulation of a particular metabolic intermediate. So this was a really cool readout for either having a gene drive, meaning red cells, or not having a gene drive, would mean white cells. Also, when the cells were gene drive cells, these red cells can't grow in media without adenine. So that was another check to make sure that they were correctly mutated by the gene drive. So we tested two different gene drives at the AID2 locus. The first one was just a guide RNA that completely knocked out the wild type AID2 gene. And this would turn the white cells, or yellow here, into red. And so the cells would become red, and they also would not be able to grow without adenine. The second gene drive we designed contained a cargo gene, a URA3 gene. And we wanted to test this system because it would be, if you wanted to spread a gene throughout a population and not just knock out a gene, we wanted to test if that was actually possible. So this URA3 gene, so these cells also become red, don't grow without adenine, but they can grow without uracil. So these cells, if the gene drive worked correctly, wouldn't be able to grow without uracil. So they get a trait with this gene drive instead of just having a knockout. So just as a refresher for the two different types of inheritance, with normal inheritance, the chance of getting the red trait would be 50-50, but in the gene drive case, the chance of getting we would hope that the chance would be much higher to get the red trait. So the ideal would be 100%. So what we did is we did these particular matings with the wild type strain and the gene drive strain, and then I did tetrad dissection. So I looked at the 4 progeny resulting from one mating. And what we found is when we looked at 15 different crosses, that all of the crosses were red, indicating that the gene drives were working quite well. And we did some different controls where you had the note in which there was no target for the gRNA. So this is where the scissors couldn't cut. And what we found is you get that expected normal inheritance phenotype where you get 50-50 white and red. And then also in a strain, in a cross where we didn't include the Cas9 protein, which is essential for cleavage, you also get a 50-50 white and red. So this was great. That meant that indicated to us that gene drives were working quite well. We also looked at the URA3 cross, and we found that those also had that red phenotype. All of the tetrads I dissected had that red phenotype. We also plated them on media without uracil. So if the gene drive worked correctly, we should see that the progeny have a URA3 gene and they can grow without uracil. And we found that they actually do. They grow very well without uracil. If you compare that to the wild type parent that didn't have URA3, it can't really grow well without uracil. It's hard to tell in these plates, but trust me, they can grow without uracil. We then did a qPCR to look at the population level. So instead of just looking at 15 crosses, we looked at thousands of crosses. And what we found is that the gene drive was biasing inheritance by over 99%. So that was great. That was really exciting. We then wanted to see if we could take these gene drives and cross them into many different wild type strains. So to show just how far these gene drives could cross into different strains. So we took this parent strain and crossed it with 7 different wild-type strains of diverse backgrounds. And what we found is a similar over 99% biasing in all the crosses that we did, which is pretty powerful. And it was very impressive that it actually worked so well. So just as a refresher, the approach that we first took was to separate the gRNA from the Cas9. But the issue with this particular approach is that these aren't complete gene drives, so that the gRNA is not actually associated with Cas9. So in a second approach, we associated the Cas9 genetically with the gRNA. However, without any other modification to the locus, this would be very dangerous, because if this was released into the population, into the wild-type population, this is completely autonomous and could spread by itself. So what we did is we recoded the locus that it was targeting, so that this complete gene drive could only target specific lab strains. So this was contained in that way. So this particular construct could only target engineered lab strains. So we designed 2 constructs using this architecture. The first one was just this plain construct using Cas9 and the gRNA as a complete drive, or a complete or autonomous drive. And the second construct was a reversal drive. And this is a really cool drive because it can reverse the phenotype of the previous drive. So in this particular, the first complete autonomous drive, it knocked out the A2 locus, as the previous drives did as well. But the reversal drive would actually remove the autonomous locus, the autonomous drive, and restore the A2 plus phenotype. So these cells would turn white again, and they could also grow without adenine. So this is just a little close-up of what's happening with the complete gene drive. So you have the Cas9 gene and the gRNA, and then this gRNA guides the Cas9 protein to cut at this particular recoded locus. So this is the area in the genome that's not found in wild-type cells. So this is a lab strain. Then this stimulates homologous recombination, and you get a replacement. So using qPCR to look at the population, we found that the gene drive was able to bias inheritance by over 99% as well. So that's great. So the complete gene drives work very well as well as the separated gene drives. And then when we took the reversal drive, so the reversal drives I think are super cool because they restore the effects of the previous drives, and they would replace the autonomous drive and restore the 82 plus phenotype. And these are super cool because if someone was to use gene drives to modify a population, it's important to know that you could reverse the change that you made. So you could use potentially reversal drives to do this. And the way they work, the way that the one we designed worked, is that the guide RNA cuts a region at the end of the complete gene drive. And this whole region of the Cas9 guide RNA and the wild 82 locus is incorporated into this region, and that's homology to replace the complete gene drive. So what happens is you get expression of the guide RNA stimulating cleavage here, and then recombination is stimulated to completely replace this locus with this locus. So in the end, you have a wild type 82 gene with the reversal drive. So that one worked very well as well. So as expected, I guess, at this point. But and the inheritance was biased by over 98%. So then what we did too is we did the tetride dissections that I showed for the other drives, and we plated them on media without adenine. And we showed that these strains grow very well without adenine. If you compare them to the complete gene drive parent and the reversal drive parent, they all grow just as well as the reversal drive parent does. This one, it does grow. It's hard to tell. This one's a little funky, but there are colonies that are growing quite well. So I think it just has a slow phenotype. So that was great. It proved that the reversal drive was working quite well. So a summary of the yeast gene drive experiment I did. We demonstrated that CRISPR-Cas-based gene drives function in yeast. We tested 2 different containment methods, and we also showed that the phenotypes could be reversed. And this was important because no one had tried to do Cas9-based gene drives in any organism before, or in yeast at least, or in any eukaryote. So this was a cool proof of concept for eukaryotes. So as a conclusion, with my PhD, I was able to develop a novel strain that incorporated oligonucleotides very well. That was UAE. I demonstrated that CRISPR-Cas systems can be used for genome engineering in yeast. And I also explored the use of CRISPR-Cas systems to bias inheritance in gene drives in yeast. So some future applications of some of the work I've done. Cas9-mediated genome engineering could be really powerful for incorporating multiple genes into genomes without selection at the locus, as I showed before, with that 100%. And then Yogi could be potentially used to modify these genes and pathways. So these two techniques could be used quite well in concert together. Also, some of the future applications of the gene drives in yeast. It's possible that you could use, we're actually doing this, people in the lab are doing this now, where you're taking multiple gene drives and doing multiple knockouts using 2 different gene drives. And this technique could be expanded even further to make a gene drive for every gene in the genome and potentially make minimal genomes using gene drives and knock out all the genes that are not essential. So if you had 2 genes, a red and a blue gene, over time in a population, you could slowly get takeover by both of the gene drives and get kind of purple phenotype maybe. And what we're doing, actually, I'm doing with a collaborator, Alex Chavez and Rebecca Shapiro, is applying this to an important pathogenic yeast, Candida albicans, to hopefully expand the double knockout library in Candida albicans, which is a yeast that's kind of hard to engineer right now. So the future of genome engineering is bright. That's how I'm going to end it. You can do all sorts of stuff. So some of the awesome things that are happening in our lab currently. So you are modifying pigs to be more fully humanized so that you could use pigs as complete organ donors. Use gene drives to make resistant mosquitoes that can't carry malaria anymore. Andy in our lab is working on that. Or you could do something as awesome and fantastical as turn an elephant genome into a mammoth genome. And people in our lab are working on that as well. So there's tons of different things you can do with genome engineering. Or at least with the elephant, get a cold-resistant elephant. That's the first goal. So I want to provide some acknowledgments to some people that have helped me along the way. So I first want to thank my committee members, Mo Cleo, Wilson Wong, Jim Collins, and James Galligan for being part of my committee, as well as my 2 universities. My university that my program is in, BU, as well as the genetics department at Harvard. They all provided such great support and help through the years. And I really want to thank George for providing such a unique environment for our lab. George is really a guiding light that guides all the projects in the lab. And it's impressive how well he can keep track of all these projects and know the literature so well. I'll always be grateful for the time that I have in the lab. And it laid the groundwork for my life as a scientist. This is George, and this is the older picture of George. I found it in a biotechniques paper. That was pretty cool. And then I had the honor of playing George in our skit for his birthday last summer. And it was one of the greatest acting experiences of my life. I'm always grateful for that. I really want to thank some people that have helped make all of this science happen. Harris Wang was one of my first mentors in the lab, and he was my first contact in the lab. And I said I wanted to work on yeast and do something like MAGE, which is this project he had originally worked on. And he said, "That's great, come work with us." And so it was awesome. He really helped form how I make experiments and do them in very efficient ways. So I'll always be grateful to Harris for that. Really want to thank Andrew Conley, who was a visiting scientist in our lab, and he worked a lot with the Yogi work that I showed in the first part. He works at VTT in Finland, and he visited our lab for I think only like 6 months, but he did so much work we did so much work together that it was just amazing. I also want to thank Alex, who's been a mentor for me with so many experiments, especially CRISPR-related ones. And yeast-related ones, and he's a really smart guy, and he has tons of awesome ideas, and he can really get the ideas done, which is it's awesome. It's great when you find that in someone where they can have good ideas and get them done. So And I also want to thank Sven and Kevin, who really introduced me to the whole gene drive field. I had never touched a gene drive until Sven came up to me and said, hey, you want to try some gene drives in yeast? I was like, all right, that sounds good. And then Kevin has been a champion of the whole gene drive field recently. And I want to thank everyone else in the lab. It's a really cool lab. It's big. So this is from George's birthday, and I think only half of these people are currently in the lab, probably less. But there's more people. So I think it goes. It's like a clock. This is new people, I think, and then this is some alums as well. I think like about half or 2/3 are current people in the lab, and then there's more new people too. So it's an amazing environment, and I get to work with the smartest people I've ever met in my life, and it's always inspiring me to be better and more creative. And everyone's so nice too. Everyone's really creative and intelligent, but everyone's really nice, and that's a rare combination, I think. It makes the lab pretty special. I want to thank a lot of friends that have helped me through my PhD. I want to thank my friend Dan, who I wouldn't have gone to grad school without his support, 9 years of support or so. I want to thank Alice and Nikolai, who are here. They're my best friend, probably. We talk about podcasts, science, everything. I want to thank John and Xavier. Xavier just left for Houston with John. They're really great listeners and super nice people. And I think Xavier is watching via the live feed, so thanks, Xavier. I want to thank Dan we have the same sense of humor, I think, and it's rare to find someone who has the same sense of humor as you. And I want to thank Rich, too, for always a good time, always having fun together. And I want to thank my cat. Really has provided support, and she always has a lot of wisdom from her 23 years of existence. She's actually Jeff Buka's cat, so I don't know if a lot of people know that, but Jeff Buka gave me his cat. That's Jeff Buka. She's so sweet. She's very old now, though. I want to thank my family so much for always inspiring me to be better. My grandparents worked so hard to provide support for their kids. And I want to thank all my aunts and uncles, especially for teaching me how to laugh at things. They're always, like my aunt Patrick and Cheryl have always helped me with my career in science as well, writing really good tips and stuff, as well as laughs. And then Leslie and Gary always providing me with a good joke. As well as my cousin Laura, who's been a great role model for me since I was like in the 4th grade. She represents what I want to be as a scientist, as well as potentially a physician in the future. And I want to thank my parents so much for first inspiring me to be a scientist, and for being there for me always emotionally, and always supporting me in anything I ever did. My dad was an electrical engineer, and he kind of taught me to have the physics background I think that I have, as well as think logically. And my mom has always been great and always been there for me emotionally. So I want to thank them. Any questions?
There are many yeast that cause infection, like
Yeah, yeah.
Could gene drives be used? Maybe not.
I think they could be, yeah, quite well. At least with some of the preliminary results with Candida, it seems that they work quite well. And anything that has some level of homologous recombination, I think you could use gene drives to some extent. So I think they could be really useful in that area.
Obligate sexual component.
Yeah, that's a very important component too. Yeah.
Do you need Cas9 expression and reversal drive for it to be functional?
So I don't know. As long as there's Cas9 expression from the previous drive, that should be enough. I've seen some experiments where Cas9 has been expressed only just transiently, and Cas9 is powerful enough that if it's there at any level, the version should happen. So I would think not. I haven't tested that, but I would think not, as long as it's present from the previous drive. So.
The EOD experiments.
Yeah.
Did you have any idea how to control for competence, like the ability of the different strains to take up oligo?
Yeah, we did a lot. I tested a lot of different techniques for transforming yeast, and electroporation across all the strains seemed to be the best for specifically oligonucleotides. That can't be, I wouldn't say that though for larger pieces of DNA. For whatever reason, oligos and electroporation go together the best. So, but for whatever reason, larger pieces of DNA, and if there is some sort of cut at the locus, lithium acetate transformation seems to be better from my experience. So, but oligos get into the cell, I found best through electroporation. So. Cool.
Okay, thank you. Again.
Thank you. Turn off the feed too. Live feed.